Hello everyone, my name is Magran Jaising. Today I am going to present the research work that I have done as part of the MS program I am undergoing at Liverpool John Moores University. The topic I have chosen is human activity recognition using sparse coding and dictionary learning. Background: early detection of autism spectrum disorder. As you all know, there is a surge in autism cases among children. Early detection can help parents and teachers to provide the necessary assistance. Currently, this process is a manual process, so this project attempts to solve this issue by performing human activity recognition in an automated way. As you all know, we have the cameras installed in camera classrooms. We can effectively use those cameras to capture the children's activities and then deploy an automated human activity recognition system to those cameras and then identify those children with autism spectrum disorder. Aims and objectives: build a simple human activity recognition system that can be deployed to edge devices like surveillance cameras, smartphones, etc. So, this is a Kinect camera. Through a Kinect camera, when we record something, we will get output in the format of 3D join points. So in this research work, first we will visualize the data set from the Kinect camera. Then we pre-process the data to reduce the features, effectively learn a dictionary, build a sparse histogram with the help of learn dictionary, classify the sparse histogram to recognize the activity. Literature review. As we started this study, we first researched on the existing research available on human activity recognition. So we have shortlisted the devices that are used in this field. So we will see the pros and cons of those devices. The first one is the sensor-based device. For example, a smart band or a smartwatch belongs to this category. The pros are they work indoor and outdoor, but they are not suitable for children and they are not cost efficient and they are battery powered, so they could be short-lived. The second category is vision-based devices. The surveillance camera is part of this. The pros are it is suitable for children since it is away from them, kept away from them, and it is cost efficient. It runs on electricity, so it has an unlimited power supply and it works indoor. The cons are it doesn't work well outdoor. The third category is radio frequency based devices. So in this, RFID tags based walls are built with the transmitter and the receiver, and the subject who is moving between these walls is tracked and the activity is recognized. So this is a very cost efficient way in doing human action recognition, but this is not suitable for children since it is not possible to build such kind of a wall in the classroom environment. And also this is battery powered, which could be short lived, and it does not work on a high range, so it is not possible to install this outdoors. The last one is device free. So in this, we are going to do the human action recognition without any devices. Here only the existing Wi-Fi devices at home can be utilized to track the human actions. So there will be a medium that will be created between these Wi-Fi devices, and if somebody is interrupting that medium, so that interruption is tracked as the human action. So this is also suitable for children. It can be implemented in the classroom environment. It is also cost efficient and it has an unlimited power source. It does not work for high range, so it doesn't work outdoor. So from these devices, it is very clear that we can use vision-based devices or device-free devices for human action, human activity recognition for our use case. Next, we did the study on the models that were used for human action recognition. We will see what are those models, and we'll also see those pros and cons of each one of them. The first one is the decision tree. The pros are it is less compute intensive and it requires less memory. The con is it does not work well with images and videos, and it has less accuracy. The second model is KNN, that is K nearest neighbors. The pros are less compute intensive and uses less memory. The cons are doesn't work well with images and videos, and it has less accuracy. The third model is support vector mission. The pros are less compute intensive, less memory required. The cons are doesn't work well with images and videos, and it's less accurate. The fourth one is dictionary learning. It is less compute intensive, less memory required. It works well with the images. It is highly accurate. The problem is with the dictionary size, since it is obtained through trial and error method. The fifth model we explored is artificial neural network. The pros are it is less compute intensive, less memory required, and high accuracy. Cons are doesn't work well with images, doesn't work well with videos. The next one is convolutional neural network. It works well with images, it has high accuracy. Cons are it is highly compute intensive and more memory is required. The last one is the recurrent neural network. It also works well with images and videos. It has high accuracy. The cons are it is highly compute intensive and more memory is required. Since our aim is to build a lightweight model which uses less memory and which is less compute intensive, by looking at these models, we can utilize dictionary learning for the feature engineering and the artificial neural networks for classification. Research methodology. Dataset description. So we will be using the MSR action recognition dataset for our research work. So this data set is created from the Kinect camera as discussed earlier, and it has around 20 action classes in it. So these are the 20 actions that are present in this data set, and 10 actors have performed these 20 action classes. And the data is available in 3D join points. So we can see here few of the sample data for easy understanding. So here the actor 1 has performed side boxing, 2-hand wave, and hand clap. Actor 2 has performed the same activities, side boxing, 2-hand wave, and hand clap. Here the actor 3 has performed side boxing, 2-hand wave, and hand clap. Dataset pre-processing. So here we can see clearly how the action is being performed by the actor, and when it is captured by the Kinect camera, it actually generates these 3D join points. So this is the actual action that is performed, but once it is recorded by the Kinect camera, this is the output that we get in 3D join points. So once we get this data set, the first step that we do is dense sampling. So what are we going to do here is, in a video file, there are multiple frames that are available. So if you just look at the single frame, you will not get a meaningful information. So if you club frames together and then look at it, then you can make out a meaning out of it. So this is what is being done in dense sampling. So instead of propagating the data as single frames, we will be combining frames together as meaningful information called subvolumes, right? So in this case, we'll be clubbing 13 frames together into a single feature vector. So like this, we will be doing for multiple videos, right? Multiple videos for that particular action, and then create this data matrix X. So once the data matrix X is created, we will be reducing the dimensions further using the principal component analysis. During the principal component analysis, we will be preserving 99% of the variance. The next step is the dictionary learning process, which is the core process in this methodology. So now we have the data matrix X in hand. So we are not going to use the data matrix X directly and do the classification. So what we are going to do is we will create the sparse matrix out of the data matrix X. The reason why we are creating a sparse representation is it is going to be the meaningful representation of the entire matrix, and it is going to be the best representation of it. And also it is going to consume very less memory compared to the whole data matrix. So for this, we are going to do this dictionary learning process. So here, from the data matrix X, we will be calculating data matrix D, that is a dictionary D, and the sparse matrix C. So D is the dictionary D, which will have atoms, which is the subset of the subvolume of actions. C is nothing but the sparse representation of the linear combination of those atoms. So how do we arrive at both of these data dictionary D and sparse coefficient C? We will be doing that using a iterative process. So in this iterative process, we have two stages called as sparse coding stage and dictionary update stage. So in the sparse coding stage, we will be using orthogonal matching pursuit algorithm. D will be randomly initialized, and with X and D, we will be able to calculate C, and penalty will be added whenever there is a positive value introduced in C. That is how the C will become a sparse matrix. The second stage that we are going to discuss is the dictionary update stage. So now, since we have both X and C in hand, we can generate D out of it. So one atom at a time is generated, and the atom is redesigned to reduce the residual error. So both these steps of sparse coding and dictionary update is done iteratively till the convergence of this equation is achieved. Here in the first part of this equation, where there is X minus DC is present, it is representing the reconstruction error. The second part of the equation, where lambda C is present, it is representing the penalty that is added to sparse matrix. Once we have the dictionary in hand, what we will do is we will generate the dictionary for all the action classes, and then we will create a combined dictionary like this. So it is called the fully learned dictionary. Once that is ready, then we will take our test file. We will do the data pre-processing, whatever we have explained earlier, and then we will create the data matrix X. So once we produce this data matrix X to the fully learned dictionary D, right, we will be getting the sparse matrix C, right? So that will be the sparse histogram. So here we can see the sparse histograms generated out of that dictionary and the data matrix X. So in this, if you see, for the action tennis swing, this histogram is generated for the actor 1, and this histogram is generated for the actor 2. Similarly, for the sidekick action, this histogram is generated for the actor 1, and this histogram is generated for the actor 2. So these two histograms, if you take, they, even though they are from different actors, they have very similar structure. Similarly, if you take the sidekick action, even though it is from different actor, they look very similar in nature because they represent the same action. In contrary, if you see the histogram generated for tennis swing and sidekick, right, they both are completely different from each other, right? The tennis swing histogram is different, The sidekick histogram is completely different. So with this characteristics, if we provide this histogram to this multi-layer perceptron, which is going to act as a classifier, we will be getting the action class predicted accurately. So in this multi-layer perceptron, we have used the MISH activation instead of ReLU activation. Results and discussion. So first we will see the test scenarios that we have created to test our model. We have clubbed all the similar actions together into two buckets as similar 1 and similar 2. So in this, similar actions like drawing a circle, drawing a tick, or drawing a X, etc., will be part of it. Then we grouped few of the actions where predominantly a particular body part is used, right? So this is the set of action where hand is predominantly used. And this is the set of action where leg is predominantly used. So this is hand predominantly used and this is leg predominantly used. So this forms another two test cases. Again, what we will do is we have grouped all the complex actions into the complex category and all the dissimilar actions into the dissimilar category. For example, golf swing and jogging in the complex are complex in nature and they are unique from each other, right? And also, if you take the dissimilar actions, examples like jogging and tennis swing are completely different from each other. So actions that are dissimilar are grouped under this dissimilar class. Once these test scenarios are created, we tested our model and we recorded our results. So this is the evaluation matrix from those results captured. So we have captured the recall, precision, and accuracy. So if you can see here, it is clearly evident that the dissimilar complex action, right? They have very good accuracy. So whether it is a dissimilar or if it is a complex action and actions that is predominantly using leg, which also falls under the complex bucket as well, are accurately classified. But when you take similar actions and simple actions, the accuracy is not that great. The inference from these test results is similar actions, the accuracy achieved is only 63%. So this is because the histograms were similar for the actions that involve similar movements. The classifier failed to classify the actions appropriately. But in case of complex and dissimilar actions, the accuracy achieved was 92 and 85%. The intention of this research work is to recognize autism spectrum disorder among children. Since most of their actions and behaviors are unique from the neurotypical pattern, this method and model will exactly suit our need. We also did a comparison of our model with the state-of-art models, which is using the MSR action recognition dataset. So we can see clearly that our model has performed as number 2 among the existing models. Conclusion and future works. We can conclude that we have built a lightweight model using dictionary learning, sparse coding, and multi-layer perceptron for human activity recognition. This model performed well for complex and dissimilar actions. It can be easily deployed to edge devices since it is using very less number of parameters and subsequently using less memory. The limitation with our work is it deals only with 3D join points, which is the output of the Kinect camera. So not all the surveillance cameras will provide that kind of an output. So this work might not be useful for cameras which are providing RGB videos. So as the future enhancements, what we can do is we can make sure that this work works for any kind of video output. For this, we can do deep 3D human pose estimation for every frame in the RGB video using skeleton-based model and extend this system to the uploaded videos and real-time live videos on the social media as well. By doing like this, we can build a real-time dictionary that can scale up gracefully for plethora of training samples available in the World Wide Web. The another enhancement that we can do for our project is we can read the depth information along with the 3D join points. By using this depth information, we can add the insights of the classroom environment, and also the children will be interacting with other children, and also they will be playing with some objects. So by getting the depth information, we can get insight of all these three parameters, which will add a lot of value in classifying their behavior. We can also enhance our method to a multimodal method by including audio input. This can be used in one-on-one sessions with the children effectively. Thank you, everyone.